Welcome to the PyKMD DMD tab. In case you want to follow along, I've loaded in the sample van der Pol system data with epsilon equal to 0 and a discretization period of 0.05 seconds. Then, I only kept the x1, x2, and x1 squared times x2 columns. Finally, I lifted with 1 time delay. First, I'd like to explain the basics of dynamic mode decomposition, or DMD. Loosely speaking, we can think of DMD as the dynamical systems equivalent of a Fourier decomposition. To be more precise, however, I should first introduce the Koopman operator, which is the backbone of PyKMD. The Koopman operator is an infinite dimensional linear operator that encodes information about the evolution of a dynamical system. Our goal is to find a matrix representation of this operator. In particular, we would like to calculate the Koopman operator's eigendecomposition, also known as the Koopman mode decomposition. Of course, we can't do computations on an infinite dimensional matrix, so we use DMD to get a finite approximation of the Koopman modes. These modes have two components, Ritz values and Ritz vectors, which are approximated eigenvalues and eigenvectors, respectively, of the Koopman operator. These modes evolve as complex exponentials, so they may have an oscillatory component and/or an exponentially growing or decaying component. These are both encapsulated in the Ritz values. We'll talk about these in more detail later. Now that we're more familiar with the goal of DMD, let's go through the different settings that are available. We have two options for this. First, we have the refined Rayleigh-Ritz, or RRR procedure, and second, we have the forward-backward refined Rayleigh-Ritz, or FB procedure. You can select both, one, or neither of these options. If you select neither, this is equivalent to Schmidt's DMD method. In this demonstration, I'll select RRR only. If RRR is selected, you'll have the option to refine your Ritz pairs. As I explained earlier, Ritz values and Ritz vectors are approximations of the Koopman eigenvalues and eigenfunctions. Often, due to numerics and model compression, the output of DMD may not be optimal. To remedy this, you can refine your Ritz vectors. In PyKMD, you can select the Ritz vectors which have the smallest residual norm, those whose Ritz values are closest to a specific complex number, those whose Ritz values are closest to the imaginary or real axis, or those whose values are closest to the unit circle. You can also specify how many Ritz vectors we seek to refine. The next option is data scaling. Since our algorithms run on computers with limited space, large differences in the scales of different observables can cause problems for accurate numerics. So sometimes it is advisable to scale components of our data to account for this. You can either scale by columns, rows, or not at all. This allows you to scale your data along the selected axis to unit L2 norm during the DMD procedure. Beware that column scaling will not impact the outcome of this procedure, but row scaling interacts with the singular value decomposition, or SVD, to give a different, although related, result. Next, you can do data centering. This allows you to shift your data to zero mean along a selected axis during the DMD procedure. You can either not center your data, or you can center column-wise or row-wise. Centering along the columns is a technique related to ergodic averaging, and can be seen as removing a known feature of our system. Centering along the rows can be seen as modifying our observables. Next, you can turn data balancing on or off. This can improve the conditioning of your data matrix, which can give more stable and accurate results for the DMD algorithm. However, be aware that if your matrix contains very small elements which are near numerical precision, this can cause complications. You also have two options for your SVD subroutine. The singular value decomposition, or SVD, is a technique used to find the most explanatory combinations of observables from the ones you provide. Then, using these combinations, we can learn an approximation of the system's dynamics. The first method PyKMD offers is the GESDD routine, which uses a divide and conquer approach. The second is a GESVD, which uses a general rectangular approach. Finally, you can select your mode for determining the numerical rank. There are 4 different ways to determine the number of modes to compute. These can be quite technical, so I'll defer to the literature in the description in case you want to learn more about the available options. Now that we've gone through the available settings, we can perform DMD. In this case, we'll just use the default options. To the right, we can see a table with our computed RITs values colored by their norm. We can also see these in the complex plane on the graph to the right. In the graph, we can view the RITs values in either the z-plane, which represents the discrete domain, or the s-plane, which represents the continuous domain. To switch between these views, you can hover over the graph and click on the buttons here. If you'd like to analyze your RITs values offline, you can download them either by clicking on the Download CSV button on top of the table, or by hovering over the graph and clicking on the Download button here. Now, let's take a minute to understand our results. As I mentioned earlier, each mode computed during DMD is an approximation of the Koopman operator's modes, and they evolve as complex exponentials. The RITs values give us more insight into this evolution. The modulus, or magnitude, of the RITs value determines the growth or decay of a mode. If outside the unit circle, a mode will grow exponentially. If inside, it will decay exponentially. If it's on the unit circle, it neither grows nor decays. The argument of the RITs value, or its counterclockwise angle from the x-axis, determines the phase difference between consecutive snapshots. You might notice that in this example, all the RITs values come in complex conjugate pairs. We can understand this by remembering that we're trying to decompose our time series data into modes that evolve as complex exponentials. Since our data is real, we want the imaginary parts of these exponential components to cancel each other out, which happens when their exponents are complex conjugates. If you're interested in learning more about DMD, please check out the resources in the description. Now that we've computed our modes, we can go to the Mode Reduction tab. Please stay tuned for a video on this. Thank you for watching, and please feel free to reach out to us at apps@aimdyne.com with any questions.